Deterministic Turing machine M such that for all x, if x belongs to L, then the number of paths of this machine M on x is congruent to -1 mod 2 to the power px, and otherwise it is congruent to 0 mod 2 to the power px. Okay. So, what are we saying here essentially? So, suppose if you take any language in parity p, what that means by definition is that there exists a non-deterministic, okay, so not only a non-deterministic, but a running in polynomial time. Okay. So, what we have is by definition, if we take a language in parity p, by definition there is a NP machine such that if x belongs to L, the number of paths of M on x is congruent to 1 mod 2 and otherwise it is congruent to 0 mod 2, right. So, that is what we have by definition. So, what we are doing here is we are essentially boosting the modulus. Okay. For any polynomial p, we are boosting it to 2 to the power p. Okay. So, that is what we are doing in this lemma. So, let us see why this can be done. So, that is what we want to ensure. So, it is not just any machine. So, this is not the parity p machine. Okay. So, there is some machine, let us say M tilde, okay, which acts as an evidence of the fact that L belongs to parity p, which has the property that chi M tilde x will be congruent to 1 mod 2 and this will be congruent to 0 mod 2. But what we will show is that we can also construct another machine M which has this nice property. I mean, why this is nice we will see later, but let us see why this is true. Okay. So, before I give the proof, let us make a small observation. Okay. So, let M1 and M2 be 2. So, whenever we talk about non-deterministic machines for the rest of the lecture, we will always mean polynomially whose runtime is polynomially bounded. Okay. So, if we have two non-deterministic machines, then there exist NDTMs, let me call them M sigma and M pi, such that for all x, the number of accepting paths of M sigma on any given x is equal to the number of accepting paths of M1 plus the number of accepting paths of M2. Okay. And similarly, we can say the same thing about, or similar thing about M pi, where the number of accepting paths are product of the two machines M1 and M2. So, why is this true? Or actually it not only gives existence, actually we can construct these machines m pi and m sigma very easily given m1 and m2. How is that? Yeah, so basically you non-deterministically decide whether to run m1 or m2 for m sigma. So, or in other words you just run these two machines in parallel. Okay. So, then the total number of accepting paths of m sigma will be the sum, and for m pi you just run them in sequence. Okay. So, here you run in parallel, and for this you run them in sequence. So, for every so first you run m1, whenever m1 accepts, then you decide to run m2, and whenever m2 accepts, then your m pi will accept. Okay. So, now consider the following function. This is a sort of a magic function, well, not magic, but okay. So, this function has the nice property that if x is congruent to 0 mod 2 to the power k for any k, then f of x is congruent to 0 mod 2 to the power 2k, and if x is congruent to minus 1 mod 2 to the power k, then f of x will be congruent to again minus 1 mod 2 to the power 2k. Okay. So, I will just leave this as an exercise, you can verify this. Okay. So, yeah. So, yeah, so I mean the first part is very easy, because anyway I will have a x square term that comes outside. Okay. So, the number of paths will be 2 to the power k times 2 to the power k, and for this minus 1, the point to note here is that f x cube plus 3x to the power 4 plus 1, okay, has x plus 1 whole square as a factor. Okay. So, I mean that is the main idea, rest is just filling out the details.
The first part would be like more strong, f x 0 mod 2.
You mean 3k?
Simply k, 2 power k.
That is all. That we I mean that is trivially we have, because we anyway have, I mean if we take the function f x to be the identity function, we anyway have that it is 0 mod 2 to the power k and minus 1 mod 2 to the power k. What we want is more stronger. So, our goal is to boost the modulus. Okay. Okay. So, yeah, so now the rest is easy, because what we do is, so let n be the parity P machine for L. Okay. So, construct a machine N1 such that for all x, okay, if chi n of x is congruent to 0 mod 2, then chi let me call this not n1 but n superscript 1. chi n1 of x is congruent to 0 mod 2 square, and if chi n of x is congruent to 1 mod 2, then chi n1 of x is congruent to minus 1 mod 2 square. Okay. So, here, so again, so we have a machine M because our language belongs to parity P, which means that x belongs to the language, or in other words, so x does not belong to the language if the number of accepting paths is even, and if x belongs to the language, then the number of accepting paths is odd. And by our construction, okay, so the construction is basically, so what is chi n1 of x? So, chi n1 of x here is nothing but so what is it? So, in terms of the function notation, if I just want to write it, it is nothing but 4 chi n of x whole cube plus 3 chi n of x whole to the power 4, right. So, the thing to be noted here is that it does not matter. So, since we are working in the field of size 2, 1 is same as minus 1. Okay. So, if x belongs to L, I can say, I mean, instead of writing it this way, I can also write that chi n of x is congruent to minus 1 mod 2. Okay. So, 1 mod 2 and minus 1 mod 2 are the same things in Z2. Okay. So, and what our what this function f tells us is, if I apply the function f to this number, it can easily be boosted to 2 to the power 2. Okay. And the reason why we can apply this is because of this observation, because what do we do to, let us say, get this part. So, we multiply 4 with so basically we construct a machine, let us say some n prime, which is the product of n with itself, and then again we consider its product with n again. Okay. So, that will give us x is cube, and then we consider, let us say, a trivial machine which has only 4 accepting paths, and we consider the product of that machine with whatever machine we got here. So, that will give us this part. Similarly, we get the other part and then we combine them. Okay. So, this combination can be
These cube machines, we run 3 or 4 of them in parallel.
3, if you run 3, if you run 4 of them in parallel, then
Rather than saying that 4 is a machine with only 4 accepting states.
oh, okay, you want to run 4 of them in parallel, yeah. So, that is basically taking this summing this 4 times, yeah, of course. So, because our ultimate goal is to come up with a machine M which has this property. Okay. So, so what we are showing here actually shows 2 things. Firstly, it shows existence of a machine, which is what you are telling, but actually what we are giving is something more stronger. We are constructing a machine M which will have this property. Okay. So, a priori you do not know. So, when you are given this machine n, which is the parity P machine for L, you do not know how many paths n has. Okay, and that is something which is which you even cannot get in polynomial time or even in parity P. Okay. The only thing that you can get in parity P is the parity of the number of paths. Okay. But what we want to show is that we can construct another machine very efficiently, which will have the property that the number of paths will satisfy this function.
Sir, I am not still convinced with the part.
Think about it, think about it. Maybe we can talk after class if you are not still convinced. Okay. Okay, so what do we want now? Yeah, so apply f. How many times do we need to apply f? To get a machine n log p. So, I will just call this, so this will be our machine m actually. And m satisfies the equations that if chi n of x is congruent to 0 mod 2, then chi m of x is congruent to 0 mod 2 to the power log p, which is nothing but 2 to the power p. Okay. And similarly, if chi n of x is congruent to minus 1 mod 2, then chi m of x will be congruent to minus 1 mod 2 to the power p of x. So, that proves the lemma. Right. So, what you can do, so that can be taken care of. So, what you can do is you go to the yeah. So, you take the floor function. Okay. So, you go to the integer which is less than log whatever 2 to the power floor of log p, and then what is left is basically p of x minus 2 to the power log to the power 2 to the power log of so whatever is the difference, p of x minus 2 to the power floor of log p of x. Okay. So, now you again use the same function, use the same function to well, the way I stated here it will not work. Yeah. So, what we can assume is that for any polynomial p, okay, you look at the next highest power of 2. Okay. So, you look at a power of 2 which is greater than p of x, okay, and you go up to that polynomial. So, that will actually suffice. So, yeah, you are right. So, if p x is not a polynomial, then this will actually not work. Yeah, but you can actually go to the next power, that will actually suffice. Okay. So, yeah, so you can do, you can look at another construction, so that instead of going from mod 2 to mod 2 square, you or maybe here from 2 to the power k to 2 to the power 2 k, you go from 2 to the power k to 2 to the power k plus 1. Okay, so that is why I said that maybe this function will not work, but I am sure that some other function will definitely work. Okay, so you can always take it to some exact polynomial p of x, but that is also not necessary. So, the way we will use this lemma, even p of x which is a power of 2 will work for us. Okay, so let us come back to the remaining part of the theorem. So, let L be a language in Bp dot parity dot p. So, this implies that there exists a parity p language L1 such that x is in L implies that the probability that x comma y belongs to L1 is greater than 2/3. So, here we are using the first definition of BPP that we gave. We do not need the stronger version, and if x does not belong to L, then the probability that x y belongs to L1 is less than 1/3. So, this is the definition of Bp dot parity dot p. So, now we will do some counting. So, let us use the lemma. So, by the lemma for all x comma y belongs to L1. So, note that L1 is a parity p machine. So, there exists a non-deterministic Turing machine M such that for all pairs x comma y such that let us say x has some length n and length of y is some p of n. X comma y belongs to L1 implies that chi m on x comma y is congruent to -1 mod 2 to the power p of n and if x y does not belong to L1, then this is congruent to 0 mod 2 to the power p n. Okay. So, because L1 is a parity p language. So, now let us define. So, we are almost there. So, let us define two functions. So, g of x is the number of good certificates for a given x. Okay. So, given an x, g of x is the number of y such that cardinality of y is p of x and x comma y belongs to L1. Okay. So, here what, so actually, so the thing is how do we get this polynomial p. So, p is basically the length of this random string. Okay. So, I should have mentioned it here. So, y has length p of x. So, that is why we chose all pairs which have this particular property, that x has some length n and y has length p of n. So, g of x is the set of all good certificates for a string x, in the sense that if x belongs to so if x belongs to L, what is g of x? All the y's such that x y belongs to L1, and since the probability of picking a y is greater than 2/3, so the size of this set is greater than 2/3 times 2 to the power p of x, because 2 to the power p of x is the total number of strings of length p of x, right. And if x does not belong to L1, this set has size less than 1/3 of 2 to the power p of x. Okay. So, g of x actually has this gap between these two types of x's. So, now let us define another function h of x, which is summed up over all y's such that cardinality of y is p of x over chi m of x comma y. Okay. So, you look at all the y's that have length p of x, okay, and for each such y you count the number of accepting paths that m has. So, m is our parity, well, it is not the parity p machine per se, but it is this machine that we have, and you sum them up. Okay. So, what can we say about h of x in terms of g of x? Okay. So, I just want to make a small correction. So, this will be some q of x. So, I will come back and fix what this q of x is later on, but we will take it up to some q of x. Okay. So, h of x can be summed up over all pairs x comma y that belong to L1 of chi m x comma y plus x comma y which do not belong to L1. Okay. So, I am just dividing it into two sets, y's which make it lie within the language and otherwise. So, what about this number? So, this is sigma So, if x y belongs to L1, we know that this is minus 1 mod 2 to the power q of n. So, we have a minus 1 plus sigma 0 and I just take the mod 2 to the power q n outside. Okay. So, this is congruent to. So, now this part is basically 0 because I am just summing up 0, and what about this part? What is this number equal to? Huh?
Greater than minus 2/3 times 2 to the power p or another.
Right, but more exactly what is this equal to? So, this is basically all those y's which make x belong to our L, or in other words all those pairs x comma y which belong to L1. So, this is exactly the number g of x, right, by definition. So, this is minus g of x mod 2 to the power q of x, right. So, now let us go back to this function h of x. So, what will be an upper bound on h of x? So, what is So, that is what, so we have not set qx yet. So, I want to set qx which is large enough. So, let us look at h of x first. So, what is an upper bound on this number? Maybe a little bit more, because this is a machine which takes string, which takes 2 strings as input, one has length n and the other has length p of n. So, it basically takes as input a string of length n plus p of n. Okay. So, its total the number of paths can be 2 to the power n plus p of n. So, I will just roughly denote that to be 2 to the power 2 p of n, okay. And I am summing it up over all y's of size again p of n. So, that is another 2 to the power p of n, okay. So, therefore, this is less than 2 to the power 3 p of n h of x, because the total number of y's which satisfy this property is 2 to the power p of n, and chi m x comma y can at most be 2 to the power n plus p of n, which is at most 2 to the power 2 p of n, okay. So, yeah, so now we can set our q's. So, we will set our q of n to be 3 p of n, okay. So, that is why I had said. So, and basically what this allows us to do is, so if we set our q large enough, this immediately implies that h of x is equal to 2 to the power q of n minus g of x. So, basically if I divide h of x by 2 to the power q of n, the quotient is 0 and the remainder is 2 to the power q of n minus g of x, because I had chosen my q of n to be large enough that it exceeds h of x, okay. So, it will never give a positive quotient, the quotient will always be 0, okay. So, that actually completes the analysis. So, now a little bit is left, okay. So, I try to finish it. Okay, so now look at the following machine. So, construct a NDTM, let us call it n tilde, as follows. Given x, what it does is guess a y of length p of x and then simulate what? Yeah, simulate m on x comma y. Yeah. So, basically I want to look at an upper bound on h of x, okay. So, are you convinced that this is an upper bound on h of x? Okay. So, h of x is greater than this number, okay. So, this number is nothing but 2 to the power q of n, by the way I defined q of n, right. So, if h of x is smaller than this number, what is the quotient that I get if I divide h of x by 2 to the power q of n? What is the quotient? Quotient is 0, right, and by the property that we have here, the remainder is 2 to the power q of n minus g of x. Okay, so it's just, so again, so the best way is always to work it out yourself. So work out the equations yourself, it will be clear. Okay, so how many paths does n tilde have? So n tilde is a non-deterministic machine. how many paths that, does it have? Huh? Some x, on some x. So, it guesses a y, right, of length p of x, and then it simulates m on x comma y. So, what are we doing here? How are we defining h of x? For all y, I am just summing up the number of accepting paths that m has on x comma y. Okay. So, this basically, I mean, the first step basically corresponds to this summation. Okay. So, I am guessing a y. So, for all different y's, I have different computation paths, and then on each of those computation paths, I am basically simulating m on this input. So, that will give me so many. So, the total number of accepting paths is h of x. Okay. So, and now by the way we defined our h of x, given h of x and so given h of x, we can compute g of x easily. Okay. And so, now how do we decide if something is in the language? So, as I said earlier, so x will belong to the language. So, if x belongs to the language, then we know that g of x is greater than or equal to 2 to the power p of n by 2. Okay. So, just keeping a very crude lower bound, and if x does not belong to L, we know that g of x is less than 2 to the power p n by 2. So, actually no, we actually know something more stronger, but that this is a crude bound on it. Okay. So, now the thing is that given any input x, we just call the sharp p function corresponding to h of x, because h is a function which corresponds to a non-deterministic machine. So, we just make a sharp p call which gives us the value h of x. Given h of x, we compute what g of x is. If g of x is greater than this number, we accept that input, and if g of x is less than that number, we reject that input. So, that is all. Okay. Anyway, I will stop here now, but so the proof is complete, but if you have any more questions or anything else, we can discuss a little bit more about it on Wednesday.